The afternoon session is called Financing Drawdown, the Role of Investment and Philanthropy. So before I introduce the next speaker, I just want to say how amazing it is to be up here after some of my heroes. Woody Tesh and Roger's films are inspiring and the books are inspiring, and it's why we're here at AREDAY, is to be inspired, to learn, to connect, and to be inspired. There's a book signing right now for Woody's old school information, and so that's going on next door. And right now I'm going to introduce to you our next speaker this afternoon, Jim Dehlsen. He's going to be talking about could the oceans be the answer? Tidal wave and wind energy. Come on up and I'll hand you the clicker and you can get right into it. Jim's doing a lot of things in technology. I'm an old wind guy. He did a lot of wind projects. He sold Zond Wind to, there's the clicker there, okay. Zond to GE, and then got into water technologies. He's doing some cool stuff with desalination. And some of you might have seen the recent social media stuff about this underwater data centers. The cooling efficiency of these is something that he's involved with. Fun fact, his wife and co-conspirator, Deanna, is in the audience, and they have been living together as a couple and changing the world for 57 years. So without further ado, I'm going to present our next speaker.
Very good, thank you. I believe there's a major missing piece that can be brought into the energy transition, and that's marine renewable energy. So far, there really hasn't been much progress in that area, but I think there's a way that we can move forward and really create an industry here in relatively short order. So that's what I'm going to take you through today. There's various models on what the transition looks like. Typically, it's something like 100% transition by 2050, 80% by 2030. 12 years from now, 80% transition is a really tall order. So wind and solar certainly are going to need to ramp up dramatically to do that. But there's another major area that can be brought on board, and that is marine renewable energy. So the starting point for that really is marine currents. Marine currents really are a slow-moving fluid, very much like wind energy. So everything that we've learned in wind energy over the last 30 years can be brought to bear. And I just go through some of the work that we did in developing various generations of wind turbines right up until 2010, when wind was really pretty much mainstream at that point. The first 20 years were a bit of a struggle because of the incentives that came and went in the United States. But overall, we continued to bring down the cost of energy and got to the point where now it's very much mainstream. So a lot of that technology is directly transferable into to technology for marine currents. And if you think about energy from the ocean, you bear in mind that everything we know about energy is pretty much where you find it land-based, where you use it land-based. Yet the other 70% of the planet are the oceans, and half of the population roughly lives along the coastline. So finding ways to use that marine energy can make a great contribution. Now, as we've transitioned from combustion energy to renewables, you look at the solar map, and it's kind of interesting because here you can see in the various colorations of the U.S. map where the solar intensity is the greatest, primarily the southwest. And then you look at wind, and that's primarily the center of the country, with some on each coast, primarily the northeast. But there's a big void in the lower right quadrant, and that is an area that doesn't have wind. Solar's a little sketchy because of the cloud cover and greater humidity. And yet, along the Florida coast, 10, 12, 15, 20 miles offshore, you have a current that is said to be something on the order of 100 times all of the rivers of the planet in terms of mass transport. Ben Franklin was the original mapper of that current. And what you have is a velocity in the current that's about 15% of a good wind site, but it's constant. And the fluid is 800 times greater than wind or than air. So you have a very dense energy resource, and the numbers that you see there in terms of power per megawatt, you're roughly 2 times more energy per megawatt in the marine current than you are with wind, and about 4 times more than solar. So for the last half dozen years, we've been working on essentially the topology of a machine that can be economic enough to be deployed in the Gulf Stream. And it looks like this. It's a marine spar structure, which is a vertical tubular structure with a buoyancy at the top and the mass, the weight at the bottom. And it's a little bit hard to see, but there's a spreader structure about midway up that tube that has a mooring system, so it immobilizes the spreader and allows the tube to be able to rotate within the spreader. And that means that this turbine can operate in a steady one-direction current, or it can go into tidal currents. Ultimately, getting these kind of technologies into the world is about reaching a cost of energy that can be competitive enough to at least be viable in a few markets. So cost of energy is the main driver in terms of how how you keep iterating on the technology and coming up with innovations to be able to get to that cost of energy. So what you can see here is that the machine that's underwater there will produce about the same amount of power as a wind turbine, the 2.5 megawatt wind turbine, which is intermittent, and in a good wind site, the two will produce about the same amount of power. But you look at the amount of structure involved, the amount of steel, which is cost, which is a key component of your cost of energy, is a lot less. But in arriving at cost of energy, it's not just the cost of the hardware, it's how much power it can produce, so power to weight, and then it's how do you deploy it. If you need big structures on the seabed or major kind of ships or big cranes, all that sort of thing can make the cost prohibitive, as the Europeans have found out. Our approach really is to tow the vessel out horizontally, and you dry connect everything on the surface. Once it's connected, you add ballast and it goes to a vertical operating position, and you're in business. So it's relatively inexpensive to deploy. And then another very key item in cost of energy is the ability to service it. So these are very much like a wind turbine. Rather than getting on board and going up to the nacelle, you go on board and go down to the drivetrain. So those 3 items is what gets you to a cost of energy that hopefully gets you in the ball game. Now, the next thing is, if we're going to try to bring a new technology on board and essentially create an industry out of that, the industry being not only marine currents, but once you get into the sea and you start generating power, wave energy will be right there behind. We're probably 3 years out on wave energy from where we are with marine current turbines. And there will be marine-based solar energy, and that's a few years out too. But the way you get an industry launched is to find a really opportune place to launch into, which would be the Gulf Stream. And between Fort Lauderdale and West Palm Beach, there's areas that are, 15 miles offshore. This enormous treasure of an energy resource flowing right out there, connected by submarine cables, very much the same way you do an offshore wind turbine project. And because of the energy density, the potential of the Gulf Stream is absolutely enormous. That inset picture shows blocks that are the Department of Interior's lease blocks for oil and gas, and more recently for wind. They're 3 miles on a site, so 9 square miles will hold 500 marine current turbines equal to 600 megawatts. 2 of those equals a pretty decent sized nuclear plant or big major coal-fired plant. So it's at a steady 24-hour/7 energy. And you can see how many blocks, and that whole thing is just a speck on the in the Gulf Stream. So it's a major resource that really needs to be brought into reality. So where it stands now is that we have a cost of energy on the marine current turbine of around $150 a megawatt hour. Sounds like a lot, 15 cents a kilowatt hour. The blue bars show where wind started, and it was well into the first decade and a half for wind that we were seeing comparable cost of energy numbers, where wind had tax benefits and it had other incentives that brought the cost down. It was well into the 1990s that we were still up in the kind of mid-teens range. So I think coming in at 15 cents a kilowatt hour equates very nicely with offshore wind that's now being deployed that's around 13 cents a kilowatt hour. And the main difference being is constant energy versus intermittent energy. And in fact, with the Gulf Stream in the summertime, there's actually a peaking factor which matches very well with the loads of the southeastern U.S. So that's really my case for moving this forward pretty aggressively now. And in terms of what kind of an impact could it make, if you look at Mark Jacobson's model, he's a Stanford guy, where what I mentioned at the beginning of this, that aiming for 100% transition by 2050 and 80% by 2030, that really is made up of a number of things, that transition. Business as usual takes you from 12 terawatts to 20 terawatts just by electrification, getting away from combustion engines to drive things, brings you down by 23%, just electrification. End-use energy efficiency brings you down another 7%. By not having to dig stuff out of the ground, transport it, spill it, clean it up, burn it, etc., you're down another 13%. So basically just those things transitioning away from carbon fuels gets you to that 11 terawatts. And then the way you fill in on that is wind has to increase some 400 to 500% during the decade of the 20s. Solar is about the same amount. Those two things really make up the lion's share of that replacement energy. There's a very small sliver in there for marine renewables. And what I did was to take my experience in terms of how fast these technologies can ramp up and layered in that yellow line So it's my best shot at what that could look like. And that, by 2030, could bring it back maybe 2027 or something. I think not an insignificant amount. But from 2050, it brings it back to the early kind of 2030s. So you could almost cut your time in half to be completely off fossil fuels at that point. And launching an industry really requires everybody to get on board. This deal is one where you have 4 states that are, just don't understand what they have off their shores. There needs to be an action, possibly a renewable portfolio standard or some kind of action to get that policy-making element to kick in big time. And if that happens, this industry could be launched. Took wind 30 years. This could be a 5 or 10 year time to get to that level, to a level of significant contribution. So that's it. Thank you.